very good handwritten notes I've shared on the WhatsApp group. So they have extra material also that are not included in your syllabus, like Davison's and Jomer's experiment from dual nature and all these. So do not study that. There's the topics that are included in your syllabus, just focus on it. And everything, whatever we have studied in the class, everything is written over there. So you don't need to make separate notes for it. That's why in the class also I was not giving much details. So this is basically energy level diagram. Same thing that I represented, no, in the form of those concentric circles. Same thing, I'm writing it here only. So this is n is equal to 1, this is n is equal to 2, n equal to 3, n equal to 4, n equal to 5, n equal to 6, and so on. The last one I'm showing, n is at infinity, because obviously we cannot draw every. Now, so rays that will be falling from infinity to the first shell, you can say, ground state also you can say. What do we say? What is the name that is given to all these? Whether it's from infinity, whether it's from the sixth shell, if it's from the fifth shell, from the fourth shell, from the third shell, or it is from the first excited state, which we say n is equal to 2. I hope all of you were present, no, in the last class. Nobody was absent? Khalid was there, Salman, Memuna was also there, Sana was there. Sneha, you were present in the last class, atoms class. Sneha. Okay, you were not present. It's fine. So these series, these will be emitting the radiations in the ultraviolet region. And what are these series known as? These are simply known as Lyman series. Fine. Then there are certain radiations that will come from infinity or from the sixth shell, fifth shell. This is just a way of representation, whatever we have studied. Or from the third to the second shell. These set of radiations, these are known as Balmer series, right? And they emit the radiation in the visible spectrum. then from infinity, or the sixth shell, or the fifth shell, or the fourth shell. N is number of shell. Atoms has no number of shells. So N is the same number of shells that are present. First orbit, second orbit, third orbit, fourth orbit, like this. So these radiations that have their final position as 3, these are known as Paschen series. And they emit their radiation. All of these now will emit their radiations in the infrared. Yes, will reach till second shell only. Sana, you were present there in the last class.
Who, me?
No, not Salman. Sana.
Oh, Sana.
You are not sure, Sana? You're not sure if you were there? Check into your notes. You must have written those things if you were present. In the last class, this lesson only, atoms. Check, you must have written, if you were present, you must have written these notes. In the last class, we didn't have any test as well. You have written the notes. Okay, then you were present, Sana. Revise nahi kara, Sana. So these set of series, these are known as bracket series. Fine. These are known as bracket series. If they have their final position, see, that's why I'm doing the revision. No, all these radiations have their initial point as something else, but final point is fixed for Lyman, for Balmer, for Paschen, for bracket. And at the end, last series that you have is the Punch series. So 6th to 5th, or infinity to 5th. This is known as the Fund series. And all of these 3 emit the radiations in the infrared spectrum. Now, one thing that I had told you in the last class, but we didn't drop any conclusion out of it, it was energy. So energy we had seen, no, energy's formula I have told you that it is minus 13.6 Z square by N square, but we are considering hydrogen, and for hydrogen Z is 1. So minus 13.6 N square electron volt. So see, for the first shell, that is N is equal to 1, energy will be minus 13.6 electron volt. For E2, it will be minus 13.6 by 2 square. That will be minus 3.4 electron volt. Class, try to remember these values, at least till the 6th orbit. It will be very helpful. When you will solve the previous year's question, then only you will notice. So this will be minus 3.4, minus 1.5 an electron. I'm not also solving this right now. I just remember all these values. At least till 6th orbit, then you can calculate. Because these are the values that are very common, and it will definitely save a lot of time, class. So 16, so it will be minus 0.85 electron volt. E5 means N is equal to 5, so minus 13.65, 5 square. So that will be minus 0.54 electron volt. And the last one you can remember is, at least till 5 you remember, 6, even if you don't remember, it's okay. That will be minus 0.38 electron volt. Why am I emphasizing? Because that will be needed in the energy level diagram. Okay, Sana. So you have seen the recorded video. That's why you're having them. That's why the notes are present. No, okay then. Good that you have at least seen the video. Only the doubt part will be left now. So wherever you are having difficulty, no, let me know, Sana. It's good that you have at least seen the recorded video. Sneha, you also watch the video. Take the recorded video. YouTube, you can directly find by yourself also. Otherwise, take it from me. At least watch the video so that you'll have an idea. Okay, you have also seen. Very good then. So see, N is equal to 1. Energy is minus 13.6. N is equal to minus 3.volt. This is all is in electron volt only. I'm not writing electron volt. Then minus 1.5, minus 0.85, then minus 0.54, then minus 0.38. At infinity, it will be 0. Energy at infinity will be 0 because 1 by infinity square will be 0. Right? This is how you make the complete diagram. And in the notes that I have given you, there the limitations of Bohr's theory are also mentioned. So here, let me just discuss with you what are the limitations of Bohr's theory. Everything is written in the notes. See, first limitation was, here I'm not writing it in detail. So for examination preference, no, refer to your notes. Right now, just understand. See, first limitation was that it was just applicable to hydrogen or hydrogen-like atoms. So what about the electron? What about the atoms that have more than a single electron? They'll not be able to satisfy all the properties and all the postulates that was given by Bohr. So that became the first limitation, right? And second limitation was, see, in the spectrum of hydrogen, which we have just drawn, which we have studied in the last class as well, not a single line was there. There were groups of lines, no? So what will happen? Every line that is coming, let's say from infinity, one ray is coming, from sixth orbit, one ray is coming, from fifth orbit, one is coming. What will happen? These are groups of closed line, and every line has a different frequency. Different frequencies will be present of all it. So that cannot explain the features of hydrogen spectrum. Third limitation that arised was that it does not explain the fact that why only circular orbits we have. Why do we have only circular orbits? Understood? Why only circular orbits should be chosen? Because elliptical orbits are also possible for rotation. Right? Elliptical orbits are also possible for revolution to occur. So there wasn't any explanation for this. So that became the limitation of it. Then one more thing. In continuously in dual nature of matter, dual nature meant what? The two nature. Dual means two. So second nature was the wave nature. One was particle nature. Second one was wave nature. But in case of Bohr's theory here, wave nature wasn't considered, though it started with that only. But then electrons exhibit wave properties also. So orbits of electrons cannot be exactly defined in Bohr's theory, right? If we are exhibiting wave properties. So that also became a very big limitation. And then spectral lines, okay, spectral line one we have discussed, no? Okay, last thing, Zeeman effect and star effect. Zeeman effect. See, Zeeman effect is what? These lines, no, the spectral lines that are present. Spectral lines are those lines only, the ray diagram which I have drawn, all the lines that are falling. So spectral lines occurrence in magnetic field. What will happen if it occurs in magnetic field? That phenomena is known as Zeeman effect. You don't need to study about it. Zeeman effect, just remember the term Zeeman effect. So spectral lines effect or spectral lines further splitting in magnetic field. We have no explanation it from the Bohr's theory. And one effect is known as Stark effect. That spectral lines explanation in electric field. That is not mentioned. Electric field and magnetic field are not considered. Plus, anything that can be difficult here is to remember, in Zeeman you have electric, or in Stark you have magnetic, like this. So make some mnemonics, make something that makes you remember that Zeeman has magnetic, Stark has electric. And yes, Bohr effect, Bohr's theory didn't explain both these two effects. So that's why these were certain huge limitations from Bohr's theory. And every theory has its limitation and certain conclusions from it. Okay, so quickly note it down. Second point of different lambda. Second point of different lambda. Second point of difference. And fourth point, are you asking this, Sana? In the limitations? Or are you asking something else? Okay, limitation. No. See, second point basically says in the spectrum of hydrogen, certain spectral lines are not single lines. See here. These are not single lines. No, you can also see in the diagram because it's not no from infinity to one it is coming and ending. No. And there cannot be any point just near to infinity. Infinity minus one is also infinity. So they are groups of line. They are groups of closed line. So every line will be having its different frequency. This spectral line will be having a different frequency. This spectral line will be having a different frequency. So Bohr's theory could not explain these fine features of the hydrogen atom. If it is having different frequency, then what is happening? Then what is the conclusion? All right, that was the limitation. And I think fourth point was regarding the wave properties. Dual nature of matter and radiation we have done. Didn't we see de Broglie's wavelength over there? De Broglie's wavelength, we had it. So that gave us the idea of that wave nature, that electrons are just not considered as particle. And in photoelectric effect, continuously we were studying particle, electrons are particle, electrons are particle. But when we studied de Broglie's wavelengths, we have seen the fact that yes, they have wave-like properties as well. But here, as electrons exhibit wave properties also. So orbits of electrons cannot be exactly defined as Bohr's theory. Understood? Bohr didn't mention this wave theory. Anywhere do you see wave nature is exhibited? No. So that becomes the limitation of it. Now understood? Yes, Anna? Okay. So two topics are there, excitation potential and excitation energy. And second is ionization energy and ionization potential. So ionization energy, I believe you people have done and used a lot in chemistry. Ionization energy gets a lot used in your chemistry. So this is exactly the same thing. Now see what is excitation energy and what is excitation potential. Is there any difference or not, or are both the same? Now see class, excitation energy is basically whatever energy is required by the electron, whatever energy is required by this electron to jump from the ground state to any one of the excited state, any one of the excited state. I'll write it down. It is the amount of energy it is the amount of energy by electron required by electron actually. Required by electron to jump from ground state. I hope you all know ground state means n is equal to 1. So from ground state to any of the excited state. It's first excited state, this is second excited state, and so on. Any of the excited states. Understood? From the ground state to any of the states. That is known as excitation energy. So see, if you want to calculate the first excitation energy. So see, first excitation energy will be what? Second minus 1. If electron is moving from the first ground state, that is the ground state, to the first excited state, n to 1. So it will be E2 minus E1. So see class, in calculations like these, no, if you remember the values that I have given you just above this, the energy's value, like E2 was minus 3.4, E1 was minus 13.6. Like this. Now your calculation becomes easy. So this becomes 10.2 electron volt. Yet, if you are practicing numericals properly, then you'll notice that even this 10.2 value, that also you will remember. Because these are certain fixed values. Because, energy level is the same. Let's take some example. Let's say second. This is the first excitation energy, Let's talk about second excitation energy. Let's say electron, ground state will remain the same. What will happen now? This is the second. This will be the third. First, second, third. From third and first, we'll be deleting. So E3 minus E1. So E3 was minus 1.51 minus 13.6. So that will be 12.09 electron. Like this, just examples. Now, what is excitation potential then? If this is excitation energy, then what is excitation potential? See, accelerating potential, this is firstly understand that this is an accelerating potential. Excitation potential. So this is an accelerating potential basically. And this accelerating potential is given to all the electrons that are colliding. So sufficient energy is there to excite the target atom by raising one of its electron from an inner to an outer orbit. So it is basically, if you see the magnitude will be exactly the same as that of ionization energy, excitation energy. Magnitude will exactly be the same. But difference is that it is the accelerating potential that is given to electrons to excite target atom. To excite the target atom by raising one of its electrons from an inner to outer orbit. C class. That in excitation energy, your ground state was fixed. Here in excitation potential, you have any inner orbit to outer orbit. This is the difference. Secondly, I was talking about potential, not potential energy, sorry, ionization energy. Ionization energy. Now see, if you completely knock an electron out of the atom, infinity to infinity, in whichever orbit the electron is present currently. Let's say this is the nucleus. 1, 2, 3. So 1, 2, 3. Let's say electron is in the second shell. The energy required to throw this out of the atom to infinity, that is known as ionization energy. And after the removal of the electron, atom is left with positive charge. And then the atom with the more amount of positive charge, this is said to be ionized. So this is the energy required to remove an electron. Remove an electron out of the atom. So here one thing is fixed. Like in excitation energy, one thing was fixed, that was ground state. You knew any energy, any other energy you were aware or not, but at least you were aware of the fact that ground state is there. Here what you're aware of, that second one is infinity. So ionization energy of hydrogen, let's say it was energy, it can be infinity minus E1. So minus 13.6, that will become plus 13.6 electron volt. So all the values that you have written, if you take out ionization energy, that will be just positive. So like this, you can remember the values of ionization energy also. Now coming to ionization potential. So same thing, the potential that is required to remove an electron. Understood. Ionization energy was energy required to remove an electron out of the atom. Ionization potential is potential required to, accelerating potential, which when given to a bombarding electron with sufficient intensity, it ionizes the targeting atom and knocking one of its electron completely out of the atom. So the way we had ionization energy, the energy that was required to remove an electron out of the atom, that is the energy required to take an electron from its ground state to outermost orbit. Similarly, you have ionization potential, but in ionization potential, it is the accelerating potential that is required. That is just the difference. Ionization potential. So it's the accelerating potential required to remove an electron or atom. The atom. All right. Note it down, class. Note down these points. Any doubts you have, clarify it. Okay, Sana, you can. Just let me know before you leave. Okay, just text me. See class, this question says that the ground state energy of hydrogen atom is minus 13.6 electron volt. So what is the kinetic energy of an electron in the second excited state? Kinetic energy in second, kinetic energy you can say, or normal energy, simple energy also you can say. So second excited state means N is equal to second excited state. N is equal to. Yes, class. What is meant by second excited state? Sneha. And Salman will leave at this moment only. He'll say he'll be having network issues as soon as I start asking questions. Yes, Neha. Khalid? Second excited state. Khalid, you're present right now?
Yes, teacher. Electron voltage is 12 point something.
No, second excited state meaning N is 1, 2, 3, what?
NS2.
Second excited state. Yes, Salman. Correct. Sana, Bamar, no series like this. N is equal to 3. N is equal to 3. Basically, you have N. Just a second, give me a second. Yes, class. Yes, 3. Understood, because ground state is 1. So first excited state. Okay. Sana minus 3.4. We are not calculating E2, Sana, no. Second excited, see, ground state is N is equal to 1. First excited state is N is equal to 2. So second excited state means N is equal to 3. That is E3. That was minus 13.6 by 3 square. That was minus 1.51 electron volt. So kinetic energy, this is total energy. So kinetic energy is negative of total energy. So it will be plus 1.51 electron. Okay, plus this is total energy. What is the potential energy of an electron in third excited state? See, total energy we know how to calculate. Third excited state mean one more ahead, that is E4. Third excited state mean N is equal to 4. So total energy will be minus, that's why I'm saying please remember these values at least till 5 or 6. In calculations, your calculation will become faster and easier. So this will be minus 0.85 electron volt. So potential energy is double of the total energy. So potential energy, it will be 2 times E4. So that will be minus 1.70 electron, right? Third part says if the electron jumps to the ground, minus 1.7. Okay, yes, potential energy, correct. So if the electron jumps to the ground state from the third excited state, calculate the wavelength of the photon emitted. It means electrons, you know how to calculate the wavelength using energy. If you know what is the energy when the electron jumps from ground to third excited state, you can easily equate it with hc by lambda. So how to find out the energy from ground to third excited state? ground to third excited state means energy will be third excited state is fourth one, E4. This was the third excited state, no? And ground state is E1. So E4 minus E1 will be equal to Hc by lambda. From here, you have to find out the wavelength. So wavelength will be Hc by E4 minus E1, which is 6.6 into 10 to the power minus 34. This is 3 into 10 to the power 8. E4 is 12.75. This is E4 minus E1 is 12.75. Or just before that, in the previous thing we had calculated in the example that we took. And this is an electron volt. No? So let us multiply it with 1.6 into 10 to the power minus 19. So let me check what is the answer. 970 angstrom. The answer that has been given is 970 angstroms. You also just cross check. This will be only the answer. Note down this question as well as the solution. Answer for this question? Answer I have written, no? Just now I have discussed. That was the answer for this question. So energy level diagram of hydrogen atom is given. 1, 2, 3, 4. So 4 orbits are given and different rays you have. So one transition is from second to first. This one is from third to first. This is from third to second, and this one is from fourth to first. This is from fourth to second, and this is from fourth to third. It says that find out the transition which results in the emission of a photon of wavelength 496 nanometer. So 496 nanometer is the wavelength that is given to you. You have to find out which transition is suited for it. And second part says which transition corresponds to emission of radiation of maximum wavelength. C class, for finding out the transition which emits in the radiation of wavelength 496 nanometer. Best way to find out is, see, if you find out for every each one. Fine. So here what is happening? If you know the wavelength, do one thing. Find out the difference between the energies. See which energy is corresponding. Then you will have an idea. 1, 2, 3, 4. We know what are the values of the energy. E1 is minus 13.6, E2 is minus 3.4, E3 is minus 1.5, and E4 is minus 0.85, right? So among this, you'll have an idea only if you find out what is the energy for this respective wavelength. So this wavelength is 496 nanometers. Let us find out the energy first. So E is equal to hc by lambda. So lambda will be, no, energy we have to find out. So lambda is given as how much? 496 nanometers. So energy will be 6.63 into 10 to the power minus 34. C is 3 into 10 to the power 8. Wavelength is 496 into 10 to the power minus 9 nanometers, right? And yes, we have to convert it. This is, let's make it into electron volt. So for electron volt, let's convert this into an electron volt. This will be now an electron volt. So around 2.5 electron volt, you will get this. Now see, now you have this around 2.5. Now it's easier for you to solve this question. How? See, E1, E2, E3, E4, you know the values. E1 is minus 13.6 electron volt. E2 is minus 3.4 electron volt. E3 is minus 1.51 electron volt. E4 is minus 0.85 electron volt. So we have to just check if we subtract any of these two, around 2.5, in which we'll get. So see, if you subtract this with this, E4 minus E2. So that will become C minus 0.85 minus 0.34. So this will be around 2.55, you can say, or 2.5 electron volt. It means the transition from 4 to 2. Check in the energy level diagram, which is the transition from 4 to 2. This one. Yes, from fourth to second one. So that's how you solve such kinds of questions. And second part says maximum wavelength. So see, which one will be having the minimum energy? Which one will have the minimum energy? So obviously from fourth to third only you will have the minimum energy, because this difference is very small and the values are also small. So if energy is minimum, maximum wavelength will be there. So this will be from second part answer. This answer for this one will be from fourth to third. This is from fourth to third. Fine, note down this. Then one more numerical we'll try to do this. Lithium and strontium. This one we'll do then. Note it down. Note down this question and then the solution for it. See, this question says that which level of doubly ionized helium, that is Li2 plus, has the same energy as the ground state energy of hydrogen atom. So this is a question actually from your NCERT only. Now, C class. For you are equating two things, ground state energy of hydrogen atom, ground state energy of hydrogen atom E1, right? That is, let's say, minus 13.6 by n square. So that is minus 13.6 by 1 square electron. And energy level of doubly ionized lithium. So see, energy, this was Z square also, and Z, and then both were equal to 1 here. Now E for lithium minus 13.6, you have Z square. So for Z for lithium, you will keep it as 3. Lithium Z is 3, so 3 square. N square, we do not know. So minus 13.6 into 9 by N square electron volt, because Z is 3 here. Now take both, equate both of them because both are given equal. So minus 13.6 is equal to minus 13.6 into 9 by n square. 13.6 cancel, n square is 9, n is equal to 3. So exactly at the third level of lithium and exactly at the third level of ground state energy of hydrogen, both are same. Fine, note down this question. Apart from this, in this lesson, you have the basic theory of Thomas model of an atom. So J.J. Thomson's pudding model you must have heard of, plum pudding model, where he thought that the whole entire, or it is also said that watermelon model. So the way in plum pudding, no, the main pudding content is there and raisins are present on it. Similarly, he thought that positively charged matter is present entirely with electrons present in between, just like the raisins in a plum pudding. But then obviously it failed because it could not explain the all those several spectral lines of hydrogen and other atoms, and scattering angle also that was not explained. That was done by Rutherford. Now, what was this scattering experiment? So all these points are written in the notes, so you can refer to those right now. Just listen. So in scattering experiment, Giger and Martson experiment. This is actually this was done by Giger and Martson, H. Giger and E. Martson. Both of them conducted this experiment. So there was a certain experiment where which element I don't remember which element it was there, but there was a radioactive source of element. So it was enclosed within a calorimeter and within a lead block that provided a narrow opening. So alpha particles from the source were collimated into the narrow beam. So alpha particles, then certain things were observed. The graph was also plotted. First thing it was observed that most of the alpha particles, now it could pass through straight through the foil. So that concluded that if it is passing straight away through the coil, through the foils, it means that there are most of the spaces within an atom is empty. That's why the radiations are able to move. Second point they were able to observe is that some alpha particles, very rare, like in 188,000, so less, they could get deflected by 90-degree or some angle. So if they are getting deflected, it means they are getting hit through a concrete object that is present. So that centralized, concentrated object in a very small region, that was the nucleus, which we commonly now refer as, that was nucleus. Then last conclusion was that some deflected nearly 180 degree, almost exactly in their entire part. So it means that if electrons are negative, it means that central portion which is present, that is positive, nucleus is positive, then only electrons are getting repelled. So these were the observations that were made through him. Then two more experiments were conducted. That was the distance of closest approach and impact parameter. Closest, I'll write there only. Closest approach and impact parameter. So no need to go into the details of closest approach and impact parameters. Just writing down the formula for it. See, closest impact means this is the central nucleus. The alpha particle is coming. It is getting deflected by 180 degree. So exactly it won't touch it, because if it is positive and this is negative, repulsion can occur from a certain distance only. So this radius that is obtained, this is known as distance of closest approach. And second thing that I'm mentioning, no, that is impact parameter. So second thing, that is impact parameter. So this also has a complete formula. I'll write it down. It is given in notes. You can copy it from here only. 2kZe square by a constant is there. The conservation energy, kinetic energy of basically alpha particle. So it has a certain value. Numericals and questions are rarely from these 2 points. One is this. Second is impact parameter. See, impact parameter is basically, this is the nucleus, let's say. The ones which are getting deflected by some angle, let's say getting deflected by theta. So this separation is known as impact parameter. Find the perpendicular distance between the velocity vector which you can take and between the center of nucleus. This is known as impact parameter. So this B is, this distance is the impact parameter. So it also has a formula 1/4 pi epsilon naught ZE square cot theta by 2 half mv square. Fine, note down these 2 points as well. That finishes off atoms. Any doubts you have in atom, go through the pages. Let me know right now. Done. Khalid, Salman, Muna, Sneha completed?
Yes, ma'am.
Okay, then let's start with nuclei. If all have completed, all right, all of you have completed. So see, in nuclei, no, some basic things of chemistry are required. So very few following terms we have to study. First term, that is basically included in the composition of an atomic nucleus. So first thing in the composition of atomic nucleus is the nucleons. This is also a small chapter. Class, from this lesson, binding energy is added recently in your syllabus, and there are high chances that question from binding energy can come, nuclear size can come. These two topics are very important. So nuclear size was there in the last year's paper also, but it's very important topic. Very easy also. The radioactivity was a portion that was difficult. But now, since radioactivity is deleted, so the lesson is very, very small lesson. See, nucleons is basically protons plus neutrons. Protons plus neutrons. That is known as nucleons. These are collectively known as. Secondly, you have to have the knowledge of atomic mass. And please, class, revise the periodic table also. There you might use it. So number of protons is known as the atomic number. Number of protons is simply known as the atomic number, denoted by this letter Z. Third thing that you have is the mass number. Mass number is protons and neutrons present in a nucleus. Right, basically you can say nucleons, you can say. Protons plus neutrons present in a nucleus. That is known as the mass number. This is also protons. Nucleons directly I can write. Protons plus neutrons, and this is denoted by the symbol A. So number of protons, see, number of protons, it will be Z. Number of electrons will also be Z. Number of nucleons will be A. That is the mass number. And number of just neutrons will be what? See, total is nucleon, that is A. Proton plus neutron is atomic number. So N will be A minus Z. It will be A minus Z. Fine. These things are required. And how an atom is represented? So we write the usual representation is A. And here that A is the atomic mass number, Z is the atomic number, and X is this is the chemical symbol. This is the chemical symbol. Like we write normally the we have been writing like let's say chlorine. 37 and 7, 35 and 17 we write 37 and 17 also, because it has same one of the isotopes. All the way we write calcium 40 and 20. Helium 3 and 2, like this. These are the examples of chemical representation, how an atom is represented. This complete is how an atom is represented, and the various constituents are also represented within it. Now here you have a concept of isotopes, isobars, isotones, and isomers. All these are involved in chemistry, but in physics, no, in some questions, you can get a value, a question where like it is mentioned what are isotones, 2 isotones are mentioned, and this is the data. So from the question only, you have to identify what all things are given. See, isotope, all these things are written in the notes, so no need to write, just understand over here. Isotopes are what? So the elements that have the same atomic number, they have same atomic number, but different mass number. Fine. Same atomic number, that is Z will be same, A will be different. Like hydrogen. Hydrogen has 3 isotopes. You must have heard of protium, deuterium, tritium, right? So all of them will be having Z same. It means H, H, H. This will be 1, 1, 1 only because this is same, Z is same. But the difference will arise in the mass 1, 2, and 3. This is a good example of isotopes. Fine. Lithium also has isotopes. Gold also has isotopes. Chlorine also has isotopes. Then comes the concept of isobars. So isobars have same mass number but different atomic number. Opposite to this. Isobars, they have same mass number and different atomic number. That is Z. Just opposite to it. For example, you can take chlorine. Chlorine, one isotope of chlorine is 37 and 17. And sulfur is also 37 and 16. So isobars. Or take the example of calcium and arsenium. Calcium is 40-20. And here you have this also as 14 and 18. This is different, but see, here both are same. So these are isobars. Then you have isotones. See, in isotones, same mass number, same number of neutrons are present. That is A minus Z is same. Same number of neutrons, isotones. Same neutrons, and neutrons are calculated by A minus Z. So A minus Z should be same. For example, take chlorine 37, 17 and potassium 39 and 19. Now, if you subtract, N is what? A minus Z. This is, here you're getting 39 minus 19, 20. Here you're getting 37 minus 17, 20. Both are same. Like this, these are known as isotones. And then you have isomers at the last. They have same atomic number, same mass number, but they are present in different energy state. Those are known as isomers. So isomers in chemistry, you study it in detail in your organic chemistry especially. But we are referring just to the nucleus right now. So same Z, same A, but different energy states. Fine, class? Understood till here? Yes, no, what?
Yes, ma'am.
Yes.
Okay. Memuna, Sneha, both of you are, I hope you're understanding. Oh, note down this part. Plus, one more thing I wanted to ask you from all of you. See, nuclei, this lesson will be, most probably this will get over in the next class, and we'll be able to start with semiconductors also. So almost the entire syllabus will be completed in the next class. One or two portion of semiconductor, if it is left, that we'll see, but everything will be completed. So let me know for the revision classes firstly, because I have to plan out your revision classes also. Do you all want a gap where you can at least see and revise everything, and then we can start revision classes at least 1 week or 2 weeks later? Or do you want immediately the revision classes? One class ends and the other class revision class. How do you all want it? Please let me know in the chat box. So at least I'll have an idea whatever all of you say. Because revision classes have to be attended very seriously. That's fine. Let me know. How do you want it? Right now, only text me. If you want a gap of week, 1 or 2 weeks. If you want for at least you can revise by yourself, collect your doubts as well, see where you are weak. Or if you want, no, you're fine with it, immediately start. See, let me know it. Yes, Sana. Sneha, I was asking. Like students have responded. Some want after the syllabus finishes. Let's say by Wednesday your syllabus finishes, or next Monday your syllabus finishes. Because maximum, even by next Monday your syllabus will finish. So, do you all want a gap, 1 week gap at least, so that you can collect your doubts and then see whatever lessons you're weak and go through the syllabus? 1 week, 2 weeks gap like this, or you want immediately after this, like the syllabus ends and the next class revision begins? That's what I was asking you. So whatever you have the opinion, like Salman says 1 week, then doubts. One says that you can start the next week. Moimuna says 1 week gap like this. So Sneha, let me know how would you prefer the doubt classes? One week, then doubts. No. So mostly students want a week gap and then the revision classes. Okay. No, Maimuna, one small topic I have to discuss with you. Do you want to leave, Maimuna? If you are in a hurry, you can leave, because just atomic mass small portion is left, and if you can attend, you can stay. That I'll do. That don't worry, Khalid. That I'll do. At the end of the class, I'll tell which chapter to revise. That I'll do. Because without that, we cannot. I'll be taking your vivas also within the class itself. You all have to revise at any cost. That will be done. Do not worry about it. That will be considered, Khalid. So just remember certain atomic masses. Because since your binding energy has been added in your syllabus, no, these will now be used. Like last year, this wasn't used anywhere, but now it will be used. Remember mass of electrons. Class, this is a very, very boring data. You have to rote learn it. 0.0055 AMU, mass of electron. Mass of proton is 1.0073. Like, see, even initially everybody has difficulty in learning. Like, I have a practice not writing, so I'm able to remember it. So even when you'll practice the questions not, then you'll not find it difficult to remember and retain all these minute values. Mass of neutron is 1.0086, and mass of hydrogen will be mass of proton plus mass of neutron, that is 1.0078 AMU. These values you have to remember. Apart from this class, there's a very important topic that is known as nuclear size. Nuclear size and nuclear density. These are very important topics, and I think question can come from this topic, because since radioactivity is also not there. This basically says that some experiments show that volume of nucleus is directly proportional to its mass number. So based on this only, questions we'll do in the next class only, but just see the theory part. 4/3 pi r cube is proportional to A. So everything, rest of the things are constant. So basically radius is proportional to A to the power 1/3. Cube root, no, we'll take R cube is equal to this. Now the constant that we get is R naught A to the power 1/3. Now R naught is what? This is a constant. This is simply a constant. No physical meaning. It has no physical meaning. Its value is 1.2 into 10 to the power minus 15 meters, which is equal to 1.2 Fermi meters. Class, this is actually a part of numerical. Like this, we are preparing ourselves for numericals of this. But class, this I have seen so many times that this comes directly to write. What is the relation between nuclear size explained in 2 marker? So you have to show all these steps and write till 1.2 Fermi. Second thing that I wanted to discuss with you is the nuclear density. This clear? This we'll do when we'll do the numericals, and it will be pretty much clear. Now, see, nuclear density. Look here. Again, I'm saying nuclear size, nuclear density theory. Just writing as it is part can also come. See, for the nuclear density, no, nuclear density will be what? It is mass by volume. The density is mass by volume. So it will be mass of nucleus by the volume of nucleus. Right, mass of nucleus by volume of nucleus. So mass of nucleus will be what? What will be the mass of nucleus? So if A is the mass number, and let's say average mass of nucleon is some m, some value, let's take m, and A is the mass number. M is what? M is average value of mass of a nucleon. Because this won't be used, that's why I'm saying. And this will again be 4/3 pi r cube. Now r cube was r naught A. Remember? See, A gets cancelled. You are left with 3m by 4 pi r naught cube. So tell me, class, A is the mass number, and this is the final formula you're obtaining. How is density related with A? Mass number, directly proportional, inversely proportional. How is it? How is density related with mass number A in the final formula? Yes, Memuna. Directly proportional, inversely proportional. How do you see it in the final formula? Yes, Memuna. Salman, can you try?
Directly proportionally.
C. Density is 3m by 4 pi r naught A cube. R naught cube. Do we anywhere see A? See, mass number gets cancelled. Here, mass number got cancelled. This clearly shows, this is a very important result, that density is independent of mass number, no directly proportional, no inversely proportional. Where do you see it? It's not in the numerator, it's not in the denominator. So clearly, nuclear density is independent of mass number. This comes to prove. How will you prove this? You just have to remember the final value. For the sake of calculation, just write it that 3 into, see, mass will be 1.67 into 10 to the power minus 27. 4 pi is 3.14. R cube, that is 1.2 into 10 to the power minus 15 whole cube. Do not solve this anywhere. Just remember the final value, that is 2.3 into 10 to the power 17 kg per meter cube. This is independent of mass. It means if you're taking calcium, if you're taking beryllium, if you're taking hydrogen, density of nucleus will everywhere for every atom, it will be 2.3 into 10 to the power 17 kg per meter cube only. This is the conclusion from it. Order is 10 to the power 17. So it means the density is very large as compared to the density of any ordinary matter. Understood? So density of nuclei of all elements is same. It is independent of mass number. Mass density of atom does not follow this rule. Mass density is different. This is nuclear density. Nuclear, the density of every nucleus. Any atom you take, sulfur you take, phosphorus you take, boron you take, nuclear density will be same. Finds in some questions you will get, calculate the value of or compare the density, nuclear densities of, let's say, germanium and silicon. So no comparison, both have same. Show this calculation everywhere, wherever the question is there. Fine, then I'll stop there, note it down, text me when you're done, then I'll stop. In the next class, we'll continue. Numericals we'll do. And one topic, that is binding energy, that we have to do. Then we'll start with semiconductors on Wednesday.